Welcome to Module 6 in this 8-module series of videos for introductory business statistics, the first in this 2-course series. This module now we're going to be looking at continuous probability distributions. You may recall from the first module where we started to talk about different types of data, different measurement scales that gave us some idea of the amount of information contained in different variables, and we differentiated between discrete variables and continuous variables. Well, Module 5 was entirely focused on those discrete variables and their probability distributions. Now Module 6, we focus our discussion on continuous probability distributions of continuous variables. So here we're going to look at really 4 different types of probability distributions. One will be the uniform distribution. Another will be the normal distribution. Probably the most commonly used, and I would guess the most understood of the continuous probability distributions. We'll look at an application of the normal. This will be normal approximation of binomials. Remember, we talked about binomial distributions in Chapter 5. Well, here we'll see how we can approximate binomial distributions or binomial probabilities using the normal distribution. And we'll also look at exponential probability distributions. Now, one of the big differences that we're going to see between the discrete probability distributions and the continuous probability distributions is when we were looking at discrete variables, we had functions f of x equals some function, and these were probability functions. So we could enter in some values to that function, and the result could be interpreted quite literally as the probability of x events occurring. So it was giving us specifically a probability. What we're going to be looking at now with all of the continuous probability distributions, we'll still have a function that is denoted f of x, but now this is a probability density function. And so what it's giving us now is no longer going to be a probability. It's going to be giving us a probability density. It's a little bit difficult to interpret specifically what that is, but when we want to calculate probabilities, what we're going to be doing now is looking at the area under a curve. So let me just quickly show you what that means. If we consider a uniform probability distribution, we had a discrete version of this where any particular probability was equal to 1 over n. So every possible outcome had an equal probability of occurring. This is like the rolling the dice or the flipping the coin example. We can also have a uniform distribution in a continuous variable, and it would look something like this, where here we have the density function, not the probability anymore. And let's say that a uniform variable is distributed between the values of, let's say we talk about the length of my videos. Maybe my videos are uniformly distributed. None of them are shorter than 5 minutes, and none of them are longer than 25 minutes. And so they're evenly distributed between those two values, that minimum and that maximum. When we're calculating probabilities now, instead of just looking at the height of that curve, that's no longer going to give us a probability. What we're going to be considering now is the area under the curve. And so that will be the probability that we're going to be interested in. So that's looking at the uniform distribution. The normal probability distribution, I'm going to guess that you've probably seen this one before. This is often the one that is referred to as the bell curve because, well, it kind of looks like a bell. And so this distribution here, we have some mean that exists in the middle, and as we move further and further away from that mean, the probability of events occurring further out from the mean is diminishing. And we see this again based on the fact that probabilities are now going to be identified as the area under the curve. Well, I can see that probabilities down here at this lower extreme from the mean, those probabilities are all very small. Similarly, probabilities out here at this extreme, they're also quite small. The highest probabilities are these regions here as we get closer and closer to the mean. Now, this probability distribution, as I said, is probably the most widely used probability distribution. It can be used to answer all kinds of different problems, and we'll see a few of those as we go through the course. Moving on to the exponential probability distribution, this one resembles very much the Poisson probability distribution. Again, we're going to be looking at a probability density function, so we're not going to have probabilities quite as explicit as we had when we were talking about discrete variables. This probability distribution now is going to look something like this. It'll have the mean value somewhere in here. This probability distribution now is used very similar to the Poisson. Remember, the Poisson probability distribution was used to estimate the number of discrete events occurring within some interval. So we had a time interval or a distance interval or something like this. And the Poisson distribution was used to estimate the probability of a number of discrete events occurring within that interval. Well, now the exponential probability distribution is almost the inverse, although mathematically it's not. But what the exponential probability distribution is saying, instead of, let's say, estimating the number of customers that will arrive at the cash register within a 1 hour period, the exponential probability distribution can be used to estimate the amount of time between customers arriving at the till. So now we're looking at the continuous variable, or the time variable, between two discrete objects or two discrete events. So instead of looking at number of people per hour, I'm looking at the amount of time between people, for example. So hopefully that distinguishes it in a simple way. So we'll actually see in one of the problems that I've put together, we'll see how we can sort of move between the Poisson distribution and the exponential probability distribution, and hopefully we'll see how those are related. So that's it for this module. We're going to go through just these, really just these two distributions, because these are both applications of the normal distribution, and in fact they're both going to be related to the standard normal distribution, which is you'll be using this distribution probably for the rest of your statistics education. It's exceedingly common. So hopefully all of this stuff will make sense to you. And again, it's laying a foundation for what is to come. So I hope that I'm able to accurately and clearly explain all of these different concepts, because you're going to be using them quite a lot in your business education. Okay, thanks for watching. Let's get started on some problems.